Well, first of all, thank you so much for the very generous introduction. So can you give me the next screen then?
Yep.
Okay. So central question, can we predict how quickly technologies will diffuse for the energy transition? You know, we're undergoing a major energy transition. If we see that wind and solar and batteries and hydrogen-based fuels are all rising quickly, but how fast can we imagine that will happen? That's the topic of the first part of the talk. Next slide. History tells us a lot about this. So here we see a history of the global energy system over the last 140 years. And the panel on the right shows you which technology supplied how much energy in each year. So you can see, if you look at that plot, that there's a green line across the top. That's traditional biomass. There's a dashed brown line, that's coal. So you can see in 1880 was the break-even point where coal reached the level of traditional biomass globally. Then coal went on to rise to become more than an order of magnitude bigger than traditional biomass. Though it's interesting, there's still that much traditional biomass being used. And we see on also oil and gas, the dashed black line and the dashed gray line, rising more quickly than the overall rate of energy growth, so that around 1970, they both reach parity with coal, roughly speaking. We see hydro rising up in blue. We see nuclear power in pink, rising quickly and then flattening out. And then we see a blue line, which is wind, a purple line, which is batteries, an orange line, which is solar energy, and a green line, which is hydrogen-based fuels. And those are strikingly different than the earlier technologies because they're rising very fast. Solar energy is rising at about 30% per year, and as you can see, it's been doing that since 1980. So one of the points is, even though solar energy might be small, if you extrapolate that exponential growth, and I should just pause to say that the scale on both of these plots is logarithmic, which means that the tick marks are powers of 10, which means that straight lines correspond to exponential growth. So even though it's still a relatively small share of the energy budget, if you just extrapolate that line, you can see that within a decade, it's going to be, it would be, if that were true, a major part. Now, the plot on the left shows what's happening, same technologies, same color code, but now costs in units of useful energy, which is a little bit tricky to do because electricity, you get more energy per watt than you do if you're just making heat. Or if you have a, say, an internal combustion engine or something like that. But so you can see there, the dashed brown line again on the bottom is coal. And you can see that although it bumps around, since over the past 140 years, the cost is about the same once you adjust for inflation as it was 140 years ago. Similarly, the dashed black line is oil. Oil is a little bit more expensive than it was 140 years ago. And now nuclear power, which once again is the pink line, starts in 1958 and rises to a level that's about 3 times what it was originally. So it got more expensive. In contrast, solar energy, the orange line you see coming down from the top, is dropping and has been dropping since the beginning at a rate of about 10% per year. Wind, the blue line, is dropping at about 6% per year. Batteries are dropping perhaps even faster than solar energy. And green hydrogen is also dropping. Not quite clear what the trajectory is going to be yet because it's still in early stages. So the point is that, you know, the future may not be like the past, but there are lessons about these in the history of different technologies for energy and the other transitions that we've seen that I think use important lessons. And in particular, if you extrapolate the cost curve, once again, you see that the cost of solar energy will, within 20 years, be substantially cheaper than other sources, assuming that trend continues. So what we've done, apart from making this plot, next slide, is to build models of costs, future costs, and future deployment of these technologies. I'll just say the past forecasts have been terrible. The IPCC, the IEA have both dramatically overestimated the costs of renewables, dramatically underestimated deployment. That's been going on for 30 years. Next slide. And this is just showing their bad forecasts. I could go into the assumptions they make that cause them to get bad forecasts. Their forecasts are getting better. I think they're closer to the truth, which means they're more in agreement with what we're saying. And next slide. Okay, I'll come back to say something about that a little later. This just blows up the diffusion of electricity generation by solar and wind. Solar is the orange one, wind is the blue one. And we're once again on a logarithmic scale, and you can see that although these are a bit bumpy, a straight line is not a bad fit for what we've seen so far. But what's going to happen in the next decade or two is hard to say, because we know these exponential growth paths can't keep going on forever. Next slide. And the traditional way to measure or to think about technology diffusion is through what's called an S-curve. You have an initial phase where the growth is slow, then it grows quickly, and then it plateaus again. One of the canonical ways to describe this is through the logistic function that I show below. And you don't need to understand this very precisely mathematically, but let me just say in the early stages, in fact, this does correspond to exponential growth. When time is in the early stages, meaning relative to some reference point t0 in that formula, then that exponential term dominates, and to a close approximation, you see exponential growth. But as you get closer to the sort of inflection point at time t0, things flip over and start slowing down. So the big question is, when are solar and wind going to start slowing down? Next slide. Now, here's an example of what happens if you just blindly try and fit S-curves using least squares. So we see solar PV deployment in the two panels on the left, and we see wind deployment in the two panels on the right. We see examples of past published papers that tried to fit S-curves to that data, and you can see that they all did a bad job, almost all. There's one that seems to have come pretty close for wind so far, but it's extremely fluky, and you can see, in fact, if you do this, that depending on exactly where you make the fit, the resulting fit that you get can be all over the place. Another thing that you see when you start doing this is that there's a strong bias. You tend to get fits that are too low and that predict asymptotic levels that are much too low. And this is a hard problem for several reasons. Next slide, please. Well, this is just illustrating our own example across the top in that top row, that if you just fit in different years, you can get dramatically different results. So we see, say on the left, a fit for Austria, including data through 2012, and then including data through 2019, and we get completely different results. Next slide. There's a lot of really bad papers out there, and so one has to be wary of this. We've actually written a critique. Next slide. I don't want to dwell on this, but some of these papers are sufficiently bad on a topic that is huge public import that unfortunately they need to be called into question. So we've had to write a paper criticizing the other guys, which I hate doing, but I think this topic's important. Next slide. Now, why is this problem so hard? First of all, the data is terrible. It's hard to come by. There's always some missing data. There are often errors, and the time series are short. the growth process is inherently non-stationary. So it's not like a nice ergodic problem in physics. You know, there's an early stage and there's a latter stage, and things are changing as you go along. The deviations from exponential growth are really small in the early stages, which means that you have a hard time telling from the data in the early stages where things are eventually going to settle. The noise is heteroscedastic, which means that the noise has different levels at different times, and the noise is autocorrelated. If you have a big fluctuation, here meaning a country experiences a growth spurt, or actually, we were looking before at global data. In fact, most of that was global data. I showed the latter one was country data, but the noise is autocorrelated. If there is a growth spurt, there tends to be growth beyond the mean for a while. And as I already mentioned, the fitting is strongly downwardly biased, and you have to correct for that. So we've been working on all these problems, trying to do it better using Bayesian methods. Next slide. And so I'm just showing this slide again, just to show you how hard it is in early stages. And we haven't added the last point or two on here, but it's still very hard to see when we're breaking away from exponential growth, which puts a lower bound, but doesn't put much of an upper bound on what's going to happen. But next slide. And now let me back up for a minute. So the question we're really asking here is, does technological growth follow any kind of deterministic law? Like this equation here, called the logistic growth process, which bacteria follow quite well. And so if we were looking at bacteria, we understand why they follow this process. Why? Well, because the rate of change is proportional to some constant K that has to do with how quickly the bacteria reproduce. X, which is the number of bacteria that are present, say, in the Petri dish at some point in time, and L minus X, which is how much is left in the Petri dish for the bacteria to expand into. So in bacteria experiments, you can solve this equation, get the logistic function, it fits extremely well. So does technology follow a process like that? Or is it just, as we say, one damn thing after another? I mean, if you ask some people, well, what about solar energy? They say solar energy got cheap because the Chinese stepped in. And then I raise my hand and say, well, wait a minute, it was getting cheap before that. Why was it getting cheap before that? Oh, well, because the Germans had the energy Wende. Okay, but what about before that? So you can keep going back, and all those factors are actually important. Policy does matter, but still it seems that there is some overall pattern that these things tend to follow. So together with Ben Wagenvoort, Joel Dyer, and Francois Lafond, we've been trying to understand this. Next slide. And so we've come up with a methodology. We gather data on 47 different technologies. We look at the technologies range from railroads to the internet. We have canals, we even have monasteries, which monastery growth follows an S-curve quite well. Maybe not quite a technology, but we've tried to find all the technologies we can where we can see that things have reached maturity, so we see the whole growth path, and tried to understand how similar are they. And so one of the things we observe in this plot is that in this plot, if the technologies followed the logistic curve perfectly, they would follow that dashed black line that you see going across the screen. And what we've done here is we took all of these 47 technologies and we rescaled them so the transition happens at overall the same rate, and that by definition, the asymptote is at 1. So in other words, to see whether the shape of the curves is the same. And what you see is after some point, the dashed vertical line we show there, things do follow pretty much the same path. And it roughly corresponds to what in the literature are called stage 2 and stage 3 of technological growth. But before that, there's a lot of diversity. And you can see that different technologies sort of lock on to this growth path at different times. So that's if we assume the logistic process, but there are other processes people have postulated. Next slide. So there's another process called the Gompertz growth process, which follows that functional form that I show here. It happens in situations where the technology also has a death process that is proportional to how long it's lived. And it turns out that things like tumors, for example, follow a Gompertz growth process quite well. Well, so when we use Gompertz, you can see that actually throughout the whole trajectory of technological change, the technologies all seem to map on to the same pattern, though it does mean we have more volatility in the later stages of the growth process, as you can see by those gray lines fluctuating in the upper right corner of the screen. So that's what the data is telling us. We're still trying to understand exactly what this means and why technologies might follow something closer to a Gompertz growth process, and understand how we can use this to predict technological change. Next slide. And well, one thing we can do, and we're pretty confident about, is if one has a prior about where the asymptote of this S-curve is, how big the Petri dish is, if you will, then, and you want to ask, when will you get to a given point on the S-curve in the future, then one can make pretty good predictions. And so here you see our prediction for solar energy. So depending on your prior, which is shown on the x-axis for where solar is going to land, you can see the time that we predict it will take to get there. So for example, at 12 terawatts of capacity, which is roughly the global capacity, then you see, or it's 100% of the current power sector, excuse me, then we should get there, we get 80% of the way there, because it's an asymptote. So, it takes, in principle, infinite to get there exactly. You get 80% of the way there by 2038. In other words, solar energy, if it follows this prediction, will be supplying 80% of our electricity by 2038. The gray bands are the 1 and 2 standard deviation bands. And this is a model that we've tested on lots of other technologies and so on. And so we have some confidence in it. My next slide, I'm going to breeze through quickly because, go ahead and change the slide. This is an attempt to predict action without knowing what the asymptotic level is. I know this prediction is wrong. It's too accurate. We're in the process of refining and testing our method. I hope to have that finished in literally a couple of weeks, but we hope to be able to really forecast where we think the technologies will be at future points in time. And one of the things I want to emphasize is we want to not just make a forecast, but have a prediction of how good our prediction is that we have tested on the 47 technologies that we've gathered by pretending to be in the past and making predictions at different points in their technological cycle. And we've already seen that for S-curves, as you get to the inflection point, then the predictions suddenly become reasonably accurate. In the early stages, they're not very accurate at all if you have to predict where the asymptote is. If you just want to predict where you're going to be, and knowing the asymptote, you can do quite well. Okay, next slide. All right, so that was about deployment. So there's some good news, if that's right. Solar energy and wind are both going to reach very substantial levels of deployment within the next 20 years or so, with some probability that stay tuned for, and I will give you a better estimate in the future. But what about costs? Next slide. So this is actually what we did first, and costs are actually easier to do. In fact, I published a forecast in 2010 saying that solar would be cheaper than coal-fired electricity by 2020. And that was viewed as a fringe forecast at the time. People said, this guy's crazy, because there you see how the cost per kilowatt hour, what I predicted they would do from the point that that was back then. And in fact, even in 2014, The Economist was saying solar power is by far the most expensive way to reduce carbon emissions. Now, how did I make this forecast? Trivially, I just plotted the data, like the data I showed you. I took my ruler, or I made it fit and just projected it forward. That's all I did. And but amazingly, other people weren't doing that. And frankly, it was forecastable decades ago, just like Moore's law was forecastable. Next slide, please. Thank you. This is an example of what we had to work hard to do better than the just ruler fit, is to understand the errors in the forecast. So I worked very hard with Francois Lafond to come up with a method to do this. And so to do this, we translated Moore's law into a stochastic process, and we actually solved for the errors as a function of time horizon for making a prediction like this. There are errors both from the diffusion, because you can see the past data over there on the left, and you can see the price coming down. It doesn't come down perfectly smoothly. It's a bumpy ride. So that's because the process is diffusive. So it's diffusing around a sort of mean benchmark. But you see the little squares, which is what's happened since, and you see what our forecast was that we made, I think, in 2013 or 14. And those little bands are, each of them represents has a probability of 5%. So it stayed well within the bands that we predicted it should stay within. And this is something we've tested on 50 different technologies, making 6,000 forecasts, sitting in the past, knowing nothing about the future, and making a forecast. Next slide. Now, okay, so this is saying what I just said. So we tested this fairly extensively. And the test is really more about testing our ability to predict the forecast errors, and as well as predicting how good the forecast itself is. So we've applied this with another group of researchers to 3 scenarios for the green energy transition. That is a very slow transition, a slow transition, and a fast transition. Next slide. In the scenario that we made up, because we just made up a scenario to start with, the key texts were solar photovoltaics, wind, lithium-ion batteries, and P2X fuels, meaning hydrogen-based fuels like ammonia. We used the method I've just told you about. We assume that fossil fuels get phased out over the next 25 years, which from the research we've done since on S-curves seems very plausible. And we tried to look at almost all of the energy systems, so not just electricity, heat, shipping, air transport. And we assumed in the electricity system that we had used hydrogen-based fuels as the backup. So we have hydrogen-based fuels that you can run through a turbine that's very much like an existing gas-fired turbine. It's a small conversion. And so that we had enough P2X fuels that we make using green electricity. We have enough fuel to run the whole energy system for a month without any sun or wind. And anyway, next slide. Well, these are examples of the forecasts that you make for solar, wind, batteries, P2X electrolyzers. Those bands out there are the sort of 90% confidence intervals for the forecasts on these 4 key technologies, showing that if we've been doing this consistently in the past, we would have done pretty well. Next slide. So what did we find? We found that a fast transition is very likely cheaper at any reasonable discount rate than the other 2 scenarios. So this kind of goes against conventional wisdom, which is that, oh, the green energy transition is going to be expensive. We all have to share the burden. Well, actually, we're going to save money. Why do we save money? We save money because solar energy very quickly makes energy cheaper than it's ever been, and also delivers a lot of other benefits. So we calculate the expected savings is about 12 trillion. We didn't construct an optimal scenario. We just constructed what we thought was a plausible scenario, one that we had enough data to compute the costs for all of the technologies. There were actually 14 altogether because we included things like hydropower, nuclear. We included all the existing technologies, and we just added stuff and basically replaced fossil fuels by solar and wind and storage and batteries. And we were extremely conservative. That is, we bent over backwards to give the other technologies the benefit of the doubt. And I want to emphasize, we made long-term forecasts. These methods work well on 5 or 10-year horizons. They don't forecast all the little bumps in the road. Next slide. Future of nuclear, I just mentioned it. We also ran a primarily nuclear scenario. It was 35 trillion more expensive than business as usual, so 46 trillion more expensive than a fast scenario. And there's a big movement afoot to make small modular nuclear reactors. I think one can show that this is extremely unlikely to succeed if you believe any of the things I've been telling you. Next slide. Roadblocks, yes, there are. Grid expansion is a big problem that has to be solved. Fossil fuel politics has been pushing that back. We have to help the energy technologies, long-term energy storage technologies, come the rest of the way down their learning curves. But my prediction is that despite these roadblocks, green energy is going to become widespread and make energy substantially cheaper than it's ever been within 20 years. Next slide. It delivers a lot of other benefits. It gives us not just cheaper energy, but lower volatility for energy prices. I could explain why if somebody's interested. Better energy security in places where it's needed, low pollution, lower environmental impact, more sustainability, and of course the big one, no greenhouse gas emissions. Next slide. So we need better models. Next slide. I want to get to the question period soon. Our model, now one of the problems I think has been that the conventional modelers here have asked the question, if we have a target that we want to hit, like 2.5 degrees Celsius, that's all the warming we're going to allow. And if there was a global master of the world who could dictate what we would do, what is the cheapest way to hit that target? So that's how the question has been framed throughout this whole literature. We're asking a different question. We're trying to predict what we think is going to happen, and then how to nudge it to make it better, and make testable, that is falsifiable predictions that we can test on what we've seen so far, test everything out of samples so we can know how good the predictions are. Next slide. So in addition to these time series models I've been telling you about, we've been building an integrated climate economics model based on different methods, but substantially based on agent-based modeling. So we're looking at the different parts of the economy. We have a model for the energy system. We have a model for production networks more generally, for households who supply labor that has occupational characteristics. So we have a model for thinking about stranded labor during the transition, for thinking about technological change and industrial strategy. We at least have the desire to make a model of agricultural and land use. We're hoping to team up with somebody, but we've been building the pieces of this model, testing the pieces individually, and then we're starting to begin to connect some of them together. Next slide. This is just an example of a prediction we've made in a fast transition in the US. We believe that we're going to see a labor boom, so more employment during the transition phase, but a substantial part of that is construction, and we do have to be careful because it's a bubble. Once we really build out solar farms everywhere, then we don't need as much construction anymore. And so we have to manage that bubble. Next slide. We built an agent-based model for energy investment. And the agents in this model are real energy and power firms like ExxonMobil or BP. Every year they may or may not invest in new assets. And so we decide how much they're going to invest. We decide which assets they invest in. We then simulate markets to find the price and quantity of energy they supply. We estimate their profits. We also build in the technology prediction models we have now so that they experience the benefits of, if, say, they invest in solar, that gets cheaper through time, which affects their decisions. And we do this year by year. And the nice thing about this, as opposed to the time series models, is now we can really think about policies and how policies affect deployment and costs in a much more robust way. So this is an example of something we're doing. Next slide. This is just a slide showing the basic loop. The model goes around. We have an energy market. We have an investment module. We create firms if needed, or firms can go bankrupt, and then we update the costs and go around this loop. And our initial condition is present set of firms. One reason we're optimistic about this model is because we have 25 years of history where we know for 90% of the energy system, all the energy plants and the firms who own those plants, we can put that together with balance sheet data to know what profits were. And so we actually have a lot of data we can test the model on. Next slide. And we've so far done Texas. Why do we do the Texas power grid? Because Texas is its own isolated power island. And we've seen that our predictions actually are pretty good for Texas. Next slide. So I'm just ending by showing you the cover of my book. This is the British version. So if you're European, the one of interest, it's with Penguin. I'm happy that I managed to get some very nice quotes from people like Larry Summers and Andrew Lowe. So a few people from the mainstream, as well as diverse others. I tried to make this book readable. So, I also have a quote from a musician who read it. Anyway, so thank you very much. And I'm looking forward to the questions.